Hi, everybody. Hey. Yes, I'm going to talk about verified thread-safe array in Rust and how you can do that. So just for the context, I'm not trying to move the state of the art. I don't think so. But it's about application of the existing techniques in Rust, in the mainstream language, in industrial language. So if you have any applications, any possible use cases for where we can apply this technique, I would be really keen to hear about that. Maybe we can try to do another case study. Yeah, so just very tiny bit about Rust borrow checker. Rust is a programming language. It doesn't have a garbage collection, so it needs some kind of mechanism that statically ensures that memory is freed at the necessary point of time, that the aliases are controlled. So borrow checker is a static analysis phase that does that, basically. And of course, it has some limitations, and sometimes people face them. And one of them was faced by a group of people who tried to translate a media decoder from C to Rust. And in C, it's called David, the media decoder. In C, you can do implicit buffer sharing easily, right? You have buffer, array, you have two threads, you operate on the same buffer, nice, because you can pass the pointer to both of the threads. But in Rust, in safe Rust, you cannot do that. And there are different ways how to do that, or how at least to do simpler things than that. One of them is you can share the array in read-only mode. This way, you can just read from the array in 2 threads, 3 threads, whatever. Or you can split the array and get 2 non-intersecting mutable views over the array and then pass them to 2 different threads. This is also safe. Or you can go and use unsafe Rust, which temporarily switches off borrow checking for a specific code section of your program. But there you're on your own, okay? It's like C. Or the last option, of course, is mutex. Maybe there are other options, but the last on this slide is mutex. But in this case, you lose concurrency, you lose parallelism. So what David media decoder did is that they implemented their array wrapper in unsafe Rust. In debug, they do runtime index checks, runtime disjointness checks, that the writes and reads are not overlapping at the same indices. But in release mode, they don't do these checks. So this is a trade-off that they had to do for a better performance. But at the same time, of course, in release, undefined behavior can happen, and data races can happen. And can we try to do both? Can we try to have both safety and performance? And one of the ways that I explored is formal verification. So one of the most popular verifiers at this point is Virus verification framework for Rust. It focuses on safe Rust, no unsafe Rust, as for now. But it has some special add-ons that extend the safe Rust and make it richer. And we are going to use these special extensions. So what's the API that we want? We want to create an array, we want to write to an array, and we want to read from an array. 3 simple operations, okay? And you can see, though, that the references here to the self object, to the array object, are shared. This means that you can pass array to multiple threads. If those are exclusive, then it wouldn't be possible. Now, the special extensions that we are going to use are called interior mutability in Rust. So in Rust, everything that is shared is by default immutable. You cannot write to it. But with Virus, there is an interior mutability thing, which is called permissioned cell. You can write, and it separates data from permissions. And now you can write to a data cell, even though you have a shared reference to it. This is how it works. So we will create an array of data elements, 2, 4, 3, 4 to 0, and we will have a map of permissions. And we have a main thread, and each permission at certain index, it points to each data element at the same index. Now we spawn the second thread, and we pass half of the permissions to the second thread. So now the second thread can operate on the second half of the data elements. The first thread can operate on the first half of the data elements. Secure. And this is, by the way, very high level. The details I can explain you after. But what we want is we want to have a map from indices to points 2, which is a permission object. And now we will propagate all of these permissions into each of the functions. So we will, instead of getting back the array when we want to create it, we will get back both the array and the set of permissions that corresponds to that array. Now, when we want to write to an array, we will require a mutable reference to the permissions map. And when we want to read it, we will require a shared reference to the permissions map. And of course, this also requires some preconditions to these functions, and namely, the permission set has to have the same ID as the array, so they have to be connected, right? You don't want to use some other permission sets for your array. Also, the permission set has to contain the permission for the ith element. So these are the preconditions. The good thing is that they are all ghosts, so they are all erased at compile time. That's nice. And so let's do some evaluation. Media decoder is too ambitious. It's a big project. I'm a small person. So let's start simple. Let's do a parallel merge sort example. Everybody knows merge sort, pretty simple algorithm. The parallel version is also not that hard. This is the idea on how it works. So we have a first thread, then we split permissions in half. Then we spawn second thread, we do the same procedure. We split the halves of the permissions in half, into quarters. Now we have 4 sets of permissions. Now we do the same thing. Now we have 8 threads. And at this point, we can stop parallelizing, because let's say we have 8 threads in our system, 8 cores. So now we do just sequential sorting. And after that, after we sorted in all of the threads, then we merge. And merging is not shown on this slide. So if we want to compare our version of parallel merge sort with something, we want to know what to compare with. And a good thing that we could compare is the safe version of the parallel merge sort that uses split at primitive that I showed before, right? So it just splits and it does the index checks, the disjointness checks. No, okay, not the disjointness checks, but just every time you split an array, it checks that the split index is in between the start and the end of the current array, and then it gives you 2 slices. This is why it does O of number of threads split index checks, because we split only, let's say, 8 times or 64 times if you have 64 cores. And also it does many index checks when we write to an array or when we read from an array. But in the verified version, there are no index checks whatsoever. So that's cool. And we want to make sure we are at least as fast as the runtime checked version. We are the same, I should say. So we are 0.8% slower. A bit surprising. So what's the diagram about? 1.0 is the time taken by split at algorithm. So it's the baseline algorithm that we are comparing to, the runtime checked version. The virus is the verified version. And split at unchecked is the same algorithm as split at, but we use the unchecked versions. So they don't do index checks. And we see that whenever we don't do index checks and use the same implementation, we are slightly faster, 1 to 2 to 3% faster. But when we use our version, which is verified, we are mostly the same, and on average 0.8% slower. Why are we slower? So one thing that is important is that runtime checks are optimized away, okay? So if we try to interfere with array read-write optimizations, then it gets 30% slower or 40% slower. So even in runtime checked version, all of these checks or most of these checks are getting optimized away because merge sort is pretty simple. You split and then you iterate from 0 to n. So compiler knows that you're not going out of bounds. And the second set of reasons could be that, first of all, the implementation is different. Because in the first implementation, we have slices that recursively get split. But in the second version, we just have one pointer to the buffer. And it gets propagated to all of the threads. The second reason, the second difference is we use arc pointer, which is atomic reference counters. We have to use it because Virus supports only standard thread spawning, but with standard thread spawning, we cannot use standard references. We can use only atomic reference counters. And the last one is some crazy, maybe unneat wrapper, which also is used by Virus, which may or may not cause some slowdown. I have some slowdown experiments after, so we can discuss it later, but I just didn't fit them in the presentation. So what about the experience? Let's see whether users like it or not. So far, there has been only one user, that's me, and I will share my experience. We don't want it to look like this. What I liked is that I was pretty confident that my implementation is correct. My implementation is memory safe, because Virus allows only safe code plus their add-ons, their interior mutability. But their interior mutability cannot compile if you are not using it incorrectly. So it might happen that my merge sort doesn't sort, that's possible. But it's not possible that it does it unsafely. So if it shuffles the bits around, it still does it memory safely. I don't prove functional correctness, but it doesn't matter what specification I give to my merge sort, it still will be memory safe. That's important. And for merge sort specifically, we can omit quantifiers, because the splitting patterns is quite simple. You just split it in half, in half, in half, in half. You don't have to operate on sets of permissions, because the slices, they are contiguous, so you can just operate on slices of permissions. This way, you don't use quantifiers, and this way, you don't use triggers and other things that come with them. But still, there are quite a lot of annotations. So there are 264 lines of code for the merge sort. Half of them is annotations, half of them is executable code. You might ask why there is any proof of memory safety if I said that memory safety does not depend on the specification and on the proof. Well, it's just because if I omit the specification, it won't compile. So I have to provide some annotations, and with them, it will compile. Otherwise, it won't infer what I want. Now, what could be improved? What could be improved is that verification frameworks can support mutable references in general, not just in some constrained positions in the first argument of the function, but in general. So you can return mutable references, you can pass them around, you can specify lifetime dependencies between them. So whatever Rust does with mutable references, it would be nice that verification frameworks would support them. Because with them, we wouldn't even have to introduce formal verification for merge. We wouldn't even have to use interior mutability for merge sort. We would just use split at unchecked and moved the index checks from runtime to preconditions. That's it. But because Virus doesn't support that, I couldn't implement it this way. And why atomic reference counter? So as I said, that there are two ways to spawn a thread in Rust. You can just send it, and then join it yourself, otherwise it won't be joined, or you can scope it, and this way you are inside this environment which will terminate the thread. Doesn't matter whether you joined it or not. And in the second case, because Rust knows the statical scope of your thread, it can make sure that all of the data that has been pushed to the thread, that has been shared with the thread, it will be shared for a static amount of time. And once the thread terminates, then you can retrieve the data and you can regain the ownership of that data. But Virus doesn't support thread scope. This is why I had to use atomic reference counters. Yeah, but getting back to motivation, we started with media decoder. Media decoder, it could not use split at mute. It had some more complicated sharing patterns. Oh, by the way, I forgot to talk about it. Well, they had more complicated sharing patterns. They could not use split at mute, but merge sort, in merge sort you can use all of these standard splitting patterns. So we want to have some studies which do more complicated sharing, more complicated concurrency. Could be David itself, but I'm happy to try other options. So if you have anything in mind, I would be down to try it on. One of them could be parallel shell sort. In shell sort, you sort subsequences of arrays in parallel, and these subsequences are not contiguous. So this could be a good example. But I have not tried this one on. But things, of course, they get more complicated with non-contiguous sharing patterns. So let's think. This is just a very recent slide. I just made it very recently. What could be the function for sharing permissions between two threads? We have an array, and we have permissions. And we want to split it in this fashion. We want this subset of permission and this subset of permission. And they are overlapping. No, they are not overlapping, but they are not contiguous. So in the preconditions, we say that, oh, P1 is disjoint with P2. And P1 and P2 are just mathematical sets. Permissions point to an array, to the array. We perform split, which is a ghost operation, just in compile time. And we get back the first set of permissions and the second set of permissions. And we make sure that both of them, they are defined by our mathematical sets of permissions that we provided. And then what else? And they both point to this array. This could be the function that people could use for arbitrary permission splitting, like a framework. And with this framework, I think people would have to prove two things. One thing is that indexes used in thread 1 belong to P1 mathematical set of indices, the same thing with the thread number 2. And this would be related to program verification, because we connect the mathematical indices that we have in mind, or actually in the program, but they are represented by ghost objects, and real indices. And we need to make sure that they are identical. But the last bit is the actual disjointness of these indices sets. And this is just mathematical, which is nice. But I have not tried to implement this function yet, so I'm about. Or if you want, you can do it. Thank you.
We'll take questions now.
Hi, this is a very nice talk, thanks. I guess I have a comment and a question. So one comment is, I think what you show at the end is exactly what you want, I totally agree. I think one way to look at this is if you could frame this in a program logic that can do this kind of reasoning, for example, in a separation logic. I think this kind of splitting is typically supported in the logic. I'd be super interested to chat about this. So we're we're keen to support mutable references in a much more general sense in the Prusti verifier very soon. So we could chat about this too if you're interested. I guess a question I have is, so at the beginning you explained what you can do in safe Rust or what your options are. I wonder if you see it this way, but it seems to me that although this is, I believe, exactly the right way to go about it, technically you're still using unsafe code, right? I mean, these functions are functions that if you were to call them in arbitrary ways, in particular, if you were to violate the preconditions, you could still cause undefined behavior.
Yes.
So technically, from the Rust standpoint, these are still unsafe functions. I really like this idea that, in a sense, they're less unsafe, right? Because you have the opportunity to use a verifier to guarantee that you're doing the right thing anyway.
Yeah, I agree. So in this case, the correctness depends on preconditions and postconditions. But what a slight advantage is that the verifier doesn't support unsafe Rust. So it's somewhere in between. We are using safe primitives from the point of view of the verifier. From the point of view of normal Rust, it's still unsafe. But we are not using, let's say, lambda Rust, which is about unsafe Rust.
Right. Okay. Thanks.
Thank you.
Great talk. I had a quick question about the performance stuff you were talking about. I know you said you could talk about it offline, but if you can say just quickly, if you were to manually go in and just delete all of the synchronized ref count operations on your arcs, what does that do to your performance?
Okay. Thanks. Okay, so first of all, benchmarks were quite noisy. Yeah. I tried to see whether the noise is significant or not. So I tried to comparing the algorithm with itself, and the null hypothesis holds. So it still says that the algorithm, if you compare it to itself, then it's the same algorithm, which is good. It's just a preliminary thing. So then I tried to add arcs and remove arcs. Let's see. Yeah, so if I remove arcs, if I use thread scope, then I get a slowdown.
Great.
So I don't know. It's a future work.
Okay, and with that interesting...
and it's weird because in this case, so we take Virus, we take our implementation, we ignore preconditions and postconditions, we remove atomic reference counters, we replace it with standard references, we get a slowdown. But if we take another implementation, which could be a raw mute pointer implementation, and we do the same procedure, so we try it with atomic reference counters and without, and the difference is marginal. It's just 3 milliseconds, so it's not even significant. So that's weird. So yeah, it's still future work.
Okay, and with that quite interesting result, we'll conclude, and let's thank the speaker again.